Today we will be talking about the DNA model. So DNA is truly the puzzle of life. In each DNA, there are pyrimidines and purines present. These are the bases we know of as Ag and Ct. So the purines are Ag, you can remember that because the silver is pure, and the pyrimidines are Ct. These are connected. You have a pyrimidine and a purine that always connect. This comes through a C or a G or a T and an A. And the hydrogen bonds help build the chains that keep the puzzles themselves together. So, for instance, a G and C bond has 3 hydrogen, whereas A and T have just 2. And the backbone is phosphodiester, so it has the phosphate group and the ester group, and these form the entire chain of the DNA. When you put DNA together, it undergoes base stacking, where each base has its pair, as shown previously, and they layer. These layers are influenced by hydrophobic forces, which kind of push the bases inward so that they don't touch the water along the outside. And then present are major and minor grooves throughout the DNA. So, for instance, if you look at this Jenga block, the bigger holes are the major grooves where there's more room per turn, and then the smaller ones are where those minor grooves are present. The backbone's attached to the bases through ribose carbons, and there's 5 main carbons that hold a specific function. The first carbon functions to attach the base to the sugar itself. The second carbon helps to distinguish DNA from RNA. It's RNA if it has a hydroxyl group, and it's DNA if it simply has a hydrogen. The 3' allows a carbon bond to form with the next 5' phosphate, and the 5' has a phosphate group attached, which then allows the 3' to attach to it so that DNA can be built. So DNA arranges in multiple different ways. So there's a handedness to it. So it's left or right based on which way is going upward. So if you look at this escalator, it is going upwards in the left direction. So it's left-handed. And then it's also antiparallel. So there are 2 strands, and these 2 strands are opposite. So they have complementary sequences, and these complementary sequences allow for those bases to have their hydrogen bonds and to match up. So salt can help in many ways. So DNA naturally has a negative backbone, and that causes destabilization when the negative charges repulse each other. And so salt works to have a positive charge basically surround this negative charge and hold it in place and help stop that repulsion because that negative charge is basically distracted by that positive. So this allows for the melting temperature of DNA to be higher, and so it makes it more stable than it was before, so it's harder to unwind. And this can help increase the hydrophobic effect, but it can also help increase DNA's longevity in warm environments. However, it can also affect how the body chooses to denature DNA if it has to. So it's going to have to go to a higher temperature. These are my resources.